Now we're going to do an example of convolution using the convolution formula that we derived last time. So last time we derived that the output of a linear time invariant system is this convolution integral that integrates over a substitute variable tau. It takes the input function x of t, but here we write it as a function of variable tau. It multiplies it at every point tau along this integral by h at t minus tau, and then it integrates over all the value taus. So in this overall equation, t is our independent variable, and it appears here in h, and then we integrate over all the input values of x of tau, and we consider the h of tau for that position. So let's do a specific concrete example. Let's have these functions for our inputs. Let's have, let's do an axes going out to 3 here, and let's have our input x be a rectangular pulse of 1 volt starting at time 0, lasting for 2 seconds. And then let's have our impulse response be something we've seen before for a exponential decay that we get when you hit an RC circuit with a impulse. We've derived that the impulse response to that last week is an exponential decay. And the output does not occur before the input, so we have h of t. This impulse response is an exponential decay. Let's write those out in equation form. X of t is going to be a unit step, subtracting a unit step delayed by 2 seconds, and h of t will do, it's 3 here, and it has a time constant of half a second, so it'll decay very quickly. And it's causal. It has a 0 value. It's a causal signal and a causal impulse response in particular, that for negative values of t, it's 0, as we've drawn it in green up above. So now what we're going to do is we're going to evaluate this integral very, very literally, but to kind of help us visualize what's happening, I'm going to draw a couple other sketches here on the right. Now, notice in the integral, we're going to integrate over the variable tau. So I'm going to make the variable that we integrate over here the tau axis. And now we're going to draw the two functions. First of all, we have x of tau. So that one just follows the tau variable. That's the simpler one in this case. So x of tau looks like this. From tau equals 0 to tau equals 2, x of tau is right there. Now, h of t minus tau is a little bit trickier. So here we have a couple things happening. First of all, we have the variable, the independent variable, the tau variable is negative. So we reflect h. And we start off with, if we just have h of negative tau, it's going to look like, let me draw that a little better. It's going to look, starting at time 0, it's going to go back and be an exponential decay this way. So that right there is h of minus tau. Now, what we have, though, is we have the independent variable t, and as we move t up, then these are going to start overlapping. So if I move t up to, say, 1.5, I get this function right here. So there's my t. I delay it. T is 1.5. And here I have h of t minus tau. So I've drawn a particular case where I have the constant t is 1.5. And since the tau axis is mirrored, or I have negative tau, that is shifting this to the right. So even though I've added 1.5, and we're used to seeing adding something in the argument moves it to the left, it's the opposite direction here. So you can substitute in values of t and tau into the original h to prove this to yourself. But the key thing here is as the parameter cap small t increases, then I'm moving that green graph of h of minus tau farther and farther to the right. So now we have a picture of what we're integrating, and that's going to help us as we evaluate this integration formula. So let's go ahead and follow it literally and substitute in x of tau. X of tau is going to be u of tau minus u of tau minus 2. So I'm just taking the definition x of t there and changing the t's to tau. And then I have h of t minus tau, so I'll substitute in that one. I have 3e to the minus 2, and the variable now is t minus tau, because that's what's that's the argument to h, and then that is times the unit step of t minus tau, because that is where the impulse begins, and I integrate with respect to tau. So now I need to simplify this, and first thing we do is we see can we simplify some of these unit steps, and the answer is yes. Since my variable of integration here is tau, these two depend only on tau. This one over here depends on t, and we're going to handle that a little later because it's a little more involved. But the fact that these unit steps are either 0 or 1, depending on the value of tau, allows me to take this integral, which goes from negative infinity to infinity, and narrow it down to only where this function is 1. And this function right here, x of tau, is 1 only when tau is between 0 and 2. And tau is the variable I'm integrating over. So I can write this integral as tau goes from 0 to 2, and then the first term drops out. It's just times 1, and I'm left with 3e to the minus 2, t minus tau, unit step t minus tau d tau. The graph here shows us what's happening for this integral as the independent variable t goes from the value 0 to t being positive values. Then this green function and the orange function overlap. And if I let this variable t go to negative values, then the green function moves to the left and does not overlap the orange function. Notice what we're doing here is we are multiplying together the x function, the orange function, and the h function, the green function. So this version here that I've drawn of h of 1.5 minus tau overlaps, and I then multiply those functions together, and I have something to integrate. But if I take this green function and I let this t parameter go to a negative value, then my transformed h function, impulse response, is over here on the left, and it's getting multiplied by the orange function having a value of 0 everywhere. So I want to divide this integral into regions that describe how the green function overlaps the orange function. And it turns out we're going to have 3 regions. The first region is when t, the shift parameter, is less than or equal to 0. Then the green function is off to the left. It does not overlap the orange function, and at least one of the functions is 0 anywhere along that tau axis. So I multiply them out, and I just integrate over 0, and I get 0. The next one we have is going to be when t goes from 0 to 2. Then I can see that in my diagram here, this edge of the green function, as it's going from 0 to 2, it is completely overlapping the orange function. This edge here always overlaps the orange function, and it overlaps going back to 0. So in that case, what I'm going to have from 0 to 2 is my region that I integrate over goes from 0 to t, because t is the right-hand side of the green function shifted over, and it is by the inequality that we have here, t is less than 2, so we know that they are going to overlap. And then the value I'm integrating is, again, 3e to the minus 2 times t minus tau, and I'm doing that integral d tau. And the final one is when the green function goes farther. So if I let the green function go 3 to the right, then the edge is here at 3, and it is decaying back this way. So in that case, I have the region of integration that I have non-zero values in starts at 0 because there's this tail of the green function, and it goes up to 2 because after 2, this part right here is cut off. So I have 0 to 2 is the region of overlap, and let's write the expression for that. Integrate from 0 to 2 of 3e to the minus 2t minus tau d tau, and that's going to be my expression when t is greater than or equal to 2. Now we notice that these two integrals are both have the same integrand, and they both have a lower limit 0, and they have the upper limit equal to the parameter t, which happens to appear inside the expression there. So we're going to work on simplifying that expression. And so we're going to have here 3 integral of 0. Now the upper limit can be 2 or t, so let's just use the parameter a as a placeholder for that, and we'll substitute it back in a minute. And now we're integrating e to the minus 2 times the quantity t minus tau. So let's break that out into two terms. So we have e to the plus 2 tau here, because it's negative times a negative. And now we see that we're integrating over tau, but we have an expression of the parameter t, so we can factor that out. And we're just integrating e to the 2 tau. So we integrate e to the 2 tau, so I get 1/2 where tau is going from the limits of 0 to the upper limit of a. So if I substitute in a, I have e to 2a, whatever that parameter is, minus, substitute in tau is 0, e to the 0, which is just 1. And now I can substitute back in to my original piecewise expression here for the output. So the first integral is the one from 0 to t, so the parameter a is equal to t, and I see I have 3/2 e to the minus 2t times the quantity e to the 2t minus 1. So let me just multiply through the e to the minus 2t. So I multiply that times e to the 2t, that's just 1, and then 1 times e to the minus 2t. So I just multiplied that term through. So I took this term and I multiplied it through, getting 1 for the first part and minus e to the minus 2t for the second part. So that's what applies when t is up to 2, but at least 0. And finally, I have for the last one, if I that one I won't multiply through. I have the e to the minus 2t, but now I substitute in the parameter a is 2, and so this becomes e to the 4th minus 1. And just as a check that this makes sense, let's look at what happens to both of these expressions at the edge here where t is equal to 2. So let's look at this one first. When t is equal to 2, I have e to the minus 4 here. So I have 1 minus e to the minus 4 times 3/2. When t is 2 here, I also have 1 e to the minus 4. So we kind of have the time shift here, and the e to the fourth looks big. But remember, this term doesn't have any effect until t gets up to 2, at which case we're starting from this term right here being e to the minus 4 and decaying further. So what does the graph look like? So if I draw out the function y of t here, it's 0 when t is less than 0, and then it has one behavior up until 2 and a different behavior beyond that. So when I can see here, I have 3/2 times this exponential decay, and if I let t get larger and larger, this exponential decay term right here is getting very small. When t reaches 2, it's e to the minus 4, so it's 1 minus a small number, so it's approaching a horizontal asymptote of 3/2. So there's 1, 2, here's the horizontal asymptote of 3/2, and by the time we get to 2, we have approached that very closely. So there's our exponential decay. Then after that, we have an exponential decay back towards 0 from that starting point. So there we go. There is our decay. And this is the waveform that we would expect for charging and discharging a capacitor, which is what the voltage X of 1 volt being on for 2 seconds is doing. Now, this procedure will work even if X is a more complicated signal, like a triangle or a sawtooth wave, or even a sinusoid. We can go ahead and evaluate that integral, and we will be able to determine exactly what the response was. This is the first method, focusing on evaluating the integral. We'll also in this class focus on a graphical view, which we've done a little bit of here, but that's what the next section goes into more depth on. And then in practice, in digital systems, you actually end up estimating this integral using a Riemann sum over very small time intervals. And there are very efficient algorithms for implementing that, and that's where we're going to be going and building up to throughout signals and systems, and then into the digital signal processing class next quarter. I recommend for your next step that you look at the MATLAB example that I have posted to go with this video lecture. It will recreate these graphs for you. It includes some additional discussion. It checks this expression, and then it also has MATLAB estimate the integral using a Riemann sum, and it shows that the graph matches our analytical solution that we did here very closely. So that's it for section 2.3. Please take a look at the MATLAB example, and then we're ready to go on to section 2.4 next, where we're going to look at calculating convolution integrals using a more graphical method.